let's do example 2. Initially, 0.92 moles of N2O4 gas is sealed in a 2 decimeter cube container and heated to 100 degrees Celsius. At equilibrium, it is found that 20.7% of the N2O4 gas has decomposed to NO2 gas. Calculate the equilibrium constant for this reaction. Okay, so I don't know if you guys know this, but N2O4 and NO2 are basically just the same gas, but the one is compressed and the other one isn't, depending on whether it's been heated up or cooled down, or if it's been compressed or expanded. So there is a reverse reaction that goes N2O4 is in dynamic equilibrium, usually with 2 NO2. Okay, but in this case they tell us that initially we have got 0.92 moles sealed in a 2 decimeter container. So as soon as I see this, I'm going to do my table even if I don't need it in the end, but let's just do it. So we got start, okay, used, made, equilibrium, and concentration. And remember, we need the concentrations because the Kc uses concentrations in the expression. In this case, the Kc is going to be the concentration of NO2 all squared all over N2O4. Okay, that's the concentration. Remember, the concentration is number of moles over volume. So what I teach my students is immediately, if we have a volume that's different from 2, I immediately write divided by 2, divided by 2, and at all the blocks that have concentration, so that I don't forget to divide by 2, which would just be a silly thing to do and you lose marks. Okay, so it says initially we've got 0.92 moles of N2O4, which means obviously that means we got 0. Oh, that's a horrible color. Let's try another one. We got 0 of NO2, right? Then it says at equilibrium, it is found that 20.7% of the N2O4 gas has decomposed to NO2. So what do we need to do? We need to find 20.7% of 0.92. So we're going to go 20.7% of 0.92. If you don't know how to do that on a calculator using percentages, it's really just going to be 20.7 over 100 times by 0.92. Okay, so it's 0.207 times 0.92. Okay, so that means that it's composed to NO2. So what we have is 0.19 moles is changed to equilibrium. Okay, has become that. That means we made 0.19. We obviously didn't use this. And therefore we've used up 0.19 moles of our N2O4, which means we can say 0.92 minus 0.19. At equilibrium, we've still got 0.73 moles of our N2O4 gas, okay? Right, so then we need to do what? We haven't finished because we need the Kc, and Kc uses concentrations. So in order to do that, we need to divide our moles at equilibrium by 2 to get our concentrations. So we've got 0.73 divided by 2, which is going to give us 0.365. Now remember, we always use 2 decimal places. So that becomes 0.37. That's our concentration. That's a 37, by the way, 7. And then we've got 0.19 divided by 2, which is going to be, so that's 0.19, and this is actually 0.095, which rounds up, because that rounds up to that, it becomes 0.1. And now we need to take these numbers and substitute them into our Kc. So we can say, right, Kc is equal to the concentration of NO2, which is 0.1, so it's 0.1 squared over the concentration of N2O4, which is 0.37, and then we pop it in our calculator. So we go 0.1 squared equals divided by 0.37, and that becomes 0.027. So the equilibrium constant Kc for this reaction is 0.027. And a typical exam question, grade 12, is then to ask you, what does this mean? And what I would say is that this reaction is not very good. It hasn't given us a lot of NO2. It's the equilibrium is lying very much to the left, or you could say that there are not many products being produced. Have a great day.